Hello everybody, welcome to the first day of the rest of your life, the day you learn the shortcuts for derivatives. You're going to be really mad at me in a couple minutes. Okay, so far all we know about derivatives is that they give the slope of a function, and we know that if we'd like to take one, we have to use this limit definition. We have to find the point that we're interested in, and we have to create that dummy point that's moved over just a bit. And we have to evaluate this whole limit, and that's usually a mess of algebra. And you say, but Miss Britton, we don't want to do that. And I say, too bad, that's how you get the slope of a function. Lies, there's shortcuts. In theory, this is what a derivative is. In practice, we're not going to use this. Okay? Now, we still have to know it, right? We still have to recognize it for what it is. Our job moving forward is to recognize this limit as the derivative of a function. But in practice, if we need a derivative, we're not going to do this. We're going to use shortcuts. And here they come. Okay. Today, I just want to go over the first two. That everything else is going to build on these two. Okay. They're not going away. They build. Okay, first one, the derivative of a constant function. Now let's think about this. A constant function like, say, this beautiful function here. Wait, I'm still writing with a white pen. This is not going to work. Okay, this function, f of x equals 5. We know that the derivative gives the slope of a function. If you've got a constant function, you have yourself a horizontal line, and you've known for a very long time that the slope of a horizontal line is 0. I don't care where this horizontal line is located. This could be a high number or a low number. It could be positive or negative. It could be a decimal. It could be a fraction. Doesn't matter. It's a horizontal line. It has a slope of 0. So your first shortcut for derivatives is very simply that if you have a function that is a constant value, its derivative is going to be 0, period. Notice here we have both notations. Here's your prime notation. So if I'm given f of x is equal to 5, I can write f prime of x is equal to 0. Or if you're given y equals 5, down here, you can report that dy dx is equal to 0. Again, even if you're given y equals 5, you could also write y prime equals 0. All of these notations are perfectly good. No, there's not one that's better than the other. It doesn't matter if you switch back and forth. Okay? What does matter is that you know that the derivative of any constant is 0. All right. Learning already. Learning already. Okay, the next one, everybody's favorite, the power rule. Okay, the power rule is good for only power functions. And let me be very clear about what we mean by a power function. We mean a base of x or some other variable, and we mean an exponent that is a number. That is very specifically what we mean by a power function. So something like x to the 7th is a power function. 7 to the x is not a power function. That's an exponential function. And even more exciting, something like x to the x. That is not a power function either. Don't worry, we're going to do this. It's even more fun. This rule is exclusively for power functions. You need a variable base. You need a numerical exponent. If you have that, you get to use the power rule. And the power rule is straightforward. Easy to remember. Okay, some of you already noticed when we were doing that limit definition that when you take the derivative of a power, it knocks it down a degree, and you are correct. Now, again, don't be mad, because we did do all those limit definitions, but here's the rule for the powers. It looks ugly, but it's not that bad. Check this out. If you have a function, x to the n, all I have to do to get its derivative is take this original exponent, multiply it down, it becomes the coefficient. The base stays the same, you subtract one off the old exponent. Done. So if I need the derivative of x to the 7th, if f of x is x to the 7th, f prime of x, I'm going to take 7, multiply it down, and instead of x to the 7, I'm going to drop it down 1, x to the 6th. Done. Now, can you imagine taking x to the 7th through the limit definition? You would have to multiply out x plus h to the 7th. That'd be fun. Okay, all right, so let me erase a little bit because I want to show you another example. Here's f of x is x to the 4th. That's this blue graph right here, right? It's U-shape. It's quartic. If I take the derivative of x to the 4th, I get f of x equals 4 when I multiply my coefficient. Multiply down my exponent to be my coefficient, x to the, knock it down 1, to the 3rd. And I want you to notice something quickly about this graph. We said that the slope of a function is given by the derivative, right? In other words, if you look at the derivative function, what you're seeing instead of x and y values is x and slope values. And look at this, look at these two graphs next to each other. When your derivative graph has negative values, look what your function's doing. All of its tangent lines are negative. When your derivative graph has positive y values, look at your function. It has all positively sloped tangent lines. And notice that when your derivative is at 0, your function has a horizontal tangent line. Derivatives do that. So they could show us just the graph of the derivative and ask us questions about the function. And as long as they were asking us questions about the slope of the function, we'd be able to answer. Okay, so I want to just go through a couple examples on how to use this, and then we'll be good to go with the power rule. Where did that come from? Okay, so first one, easy peasy, right? I have x to the 3rd. Everybody knows it's a power function. I have a base of x. I have a number as my exponent, so I'm going to multiply it down, keep my base, knock it down 1, 3x squared, done. Okay. That's as simple as they get, right? Okay, now sometimes they're still this simple, but they just get to looking less simple. Okay. Something like this, x to the square root of 7. Okay. At first glance, you're like, oh, what's going on? But again, I'm not worried about this. This is a number. It might not be the cutest number you ever saw, but all it is a number. So I'm going to use the power rule on it. I have a base of a variable, I have a number as an exponent. I'm using the power rule. So I'm going to multiply down my root 7, my original exponent, and then I'm going to have x to the, and I need to take 1 off of this. And don't go pick up your calculator. All I'm going to do is write root 7 minus 1, period. Done. If you put a decimal up there, you're putting an approximation, and we don't want that. Just root 7 minus 1, and you're done. Here's another one that looks a little suspicious. At first glance, you might say, hey, there's 2 letters there. Nah. E is a constant. Don't let this trick you. E is a number. It's 2.71828 and a bunch of other ones we don't need to talk about. Okay. All I have to do to get the derivative of this, multiply the original down, e, x to the e minus 1 is all I'm going to write. Okay. It works on negatives too. In this function, I've got x to the negative 5th. Okay, this is a base. The base is a variable. The exponent's a number. I'm using the power rule. So I'm going to multiply down my negative 5. X to the, this time I have to subtract 1, and I'm subtracting from negative, so be really careful. When I take negative 5 minus 1, I get negative 6. Okay, that can be rewritten if you so choose as, I have to write over here so I don't write on my own face, negative 5 over x to the 6th. If you so choose. Now, you may not choose, and if it's open-ended, I probably wouldn't choose. But if you're about to do something with this, you're going to need to simplify it probably, or if it's multiple choice, they're probably going to simplify it. So just be aware of those negative exponents and what you can do with them. Okay, now, another little kind of twist on the power rule is called the constant multiple rule. And the constant multiple rule says this. If you have a function that's differentiable, and there's a constant sitting in front of it, you can go ahead and take the derivative of your function and just let the constant sit there, and then when you're done, you can multiply the constant back through. Okay? This is what that looks like in math speak. Okay? It says if you have the derivative of a function, they're calling it u, multiplied by some constant. Leave the constant sitting there, take the derivative of your function, and when you're done, the constant will still be sitting there. So it doesn't matter what this is. We're going to take the derivative of it, and then we're just going to leave the constant sit there. For example, let's take that x to the 7th again, okay? But instead of just x to the 7th this time, it's going to be 5x to the 7th. What this rule is saying is, if you want to get y prime, leave the 5 sit there. Just leave it be. Take the derivative of x to the 7th, so that's 7x to the 6th. And then now in the front you have 5 times 7, so you can just multiply them, 35x to the 6th. Now for me, I don't really think of it as two separate rules. I just think of it as, look, whether there's a number out front or not, if I want to take the derivative of this, I am multiplying my old exponent down. If there's a coefficient there, multiply by it. So 7 times 5 is 35. X to the, I'm reducing this, 6th. Okay. So that's your power rule. Again, be very careful. We're going to see all kinds of functions that have exponents. That doesn't necessarily mean they're simple power rule functions. But if all you have is a single variable raised to a number, you've got a power function, you can use the power rule. Okay? Tomorrow we'll do some practice on that. Have a good night.